we have a system with two wagons, wagon A and wagon B. And they're both going towards the right. A is going at 3 meters per second and B is going at 2. MA has a weight of 100, MB has a, mass of 100, and MB 70 kilogram. Obviously, A is going faster than B, so A is going to catch up and is going to bump into B. But they're telling us that after collision, they're going to become coupled. That means that we're dealing with a sticky situation. They're going to stick with each other after collision, which means that we're dealing with a completely inelastic collision, which implies that the final velocity of both system A and B are going to be the same. And that's what the question is about. So obviously, we have identified the fact using the keyword couple that we're dealing with a completely inelastic collision. Therefore, we cannot use energy conservation law. Energy is not conserved. Therefore, we cannot use it. But we know that we can always use momentum. This is obviously a one-dimensional problem. So as usual, back to chapter 2, let's pick a coordinate system. I'm going to pick my axis x such that every vector that goes towards the right is positive, every vector that goes towards the left is negative. And I'm going to write momentum conservation law. The sum of all the momentum initial is equal to the sum of all the momentum final. And in this case, this refers to a one-dimensional case. All the momentum initial in x is equal to the sum of all the momentum final in x. Okay, so it's like Newton. Sum of force is equal to 0, sum of force is equal to ma, and then we're going to project this vector equation into two dimensions, x and y. In this case, just x. So we have two systems, system A, system B. Both have masses, therefore we need to consider the momentum of each. We're therefore going to have the initial momentum of object A in the x direction. We now have three subscripts, plus initial momentum of object B in the x direction. And then we're going to duplicate this in the final. So I'm going to replace all my I with final. Or before collision, left-hand side, after collision, right-hand side. Okay. So therefore, I have MA, V, I, AX. MB, V, I, BX. MA, V, final, AX. MB, V, final, BX. Subscript are crucial here. Now let's look at each vector. We're not dealing with forces, now we're dealing with velocity. Same thing, it's back to chapter 2. If I decided to go positive towards the right, obviously the initial velocity of object A is positive because it goes towards the right. So now let's use our coordinate system and let's write down the scalar version. And in this chapter, this is the only chapter, I would strongly suggest that you throw numbers right off the bat. This will simplify solving a 2x2 much easier. So MA is 100 times the velocity, which is positive 3. Next, MB is 70. Now let's look at the initial velocity of object B before collision. It's going towards the right, therefore positive 2. This is where completely inelastic collision comes in. We know that those two will couple, therefore they have a final velocity which is the same. Therefore, let's give them the same name, V final. And we can even factor it out. Therefore, we have 100 times V final plus 100 times V final. Same V final. In this particular case, it is obvious that the final velocity of both systems is also going towards the right. just by physical constraint. Therefore, I chose positive sign. Whoops, and this should be 70. Hence, on the right-hand side, I end up with 170 VF. And therefore, we can solve for VF to be 440 divided by 170. Bang!